Good morning to every of you. First of all, I would like to introduce these training sessions better than starting introducing myself, that I'm going to do a little bit later after some slides. This is some training sessions regarding two projects, European projects, the Mari4Yard and the PeneloPe, which we will speak a little later about them. So what I would like to start is with introducing AIMEN. What is AIMEN? AIMEN is a multi-sector innovation and technology center that develops research and developing innovation activities. And it provides as well technology services. We can see here in this presentation the two divisions that are dedicated to these tasks. The task I told you. And these services to the industry fields of materials, advanced manufacturing processes, and digitalization and sustainability. We are experts in these different technologies. We can see here in the both divisions, for example, laser technologies, additive manufacturing, welding and joining, advanced composites, smart manufacturing, etc. We are experts. We have people working here which are experts in very different technologies, and we are increasing our skills on the people who is working with new technologies. And the milestones of the AIMEN as a company started from in 1967, so far. The first one milestone is in 1995, where we started working in the Armando Pregue building here in Porriño. At the beginning, AIMEN was a small lab in the School of Engineering here in Vigo, but we started at Porriño in 1995. There's another milestone is when we were recognized like an innovation and technology center in 1998. In 2022 was the creation of the pilot joining technology plant here in Porriño. In 2024, we were recognized to start with a new building here in Porriño, the Laser Center Technology Research Plant, which opened finally at in 2014. AIMEN was 50 years associated with innovation in 2017. Finally, we are now in 2024 here. About the PeneloPe and the Mari4Yard, these both are two European projects funded by the Horizon 2020 Research and Innovation Program. The first one, the PeneloPe, is a project focused on the closed-loop digital pipeline for flexible and modular manufacturing of large components in industry in general. And the second one, the Mari4Yard, is more focused in shipyards. It's a project that aims to implement a portfolio of work-centered solutions of different technologies, focused on small and medium enterprises. Okay. What I want to present you as well to introduce is about the AIMEN Didactic Factory, which is aiming to training and upskilling capabilities, enabling the workforce transition towards the Industry 4.0, and as well a general purpose test bed for assisting in industry adoption of digital telecentric solutions in Industry in the new industry of 5.0. This is the timetable of these two sessions divided in 2 days. The first day, we will have a training session about the industrial robots programming. I will present it. Afterwards, in the middle half of the day, we will have the second session about welding with collaborative robots, which will be presented by Canonical Company, which collaborates with AIMEN here in these training sessions in these two European projects as well. And for the second day, for tomorrow, we will have several training sessions focused, for example, the first one is focused on introduction, collaborative robotics and safety. Another one is the introduction to hand guiding applications. And finally, the introduction to cutting applications with cobots. All of them will be mixed with several practical demonstrations, of course. And that's all. I think I can go ahead and start with this the first training session. The first training session is about industrial robots programming. As I told you before, I would like to introduce myself now. My name is Isidro Fernandez, and I'm a technical engineer in automatic and electronics. I studied here in Vigo, in the University of Vigo. I worked at AIMEN for 12 years. And my background is about all regarding the industrial robots, for example, designing robot cells, programming, helping to integrate the robot with other equipments and devices, and so on. Okay, so let's go and start with this first training session. The contents. These are the contents of this training session. We will start with the robot system, speaking about what's a robot, an industrial robot, which are the components regarding this, the robot art configuration as well, different robot applications that usually the industrial robots are working in, which are the processes the robot should be more focused on to work on, as well on different technologies on how to program these kind of robots. Afterwards, we will see how the robot moves within a 3D space. I will give you some concepts regarding the robot movement, okay, that are very important as well afterwards about the robot's programming. We will see as well how to move a robot. We will see the different ways we can start to move a robot. The different robot types, movement types. And afterwards, we will go downstairs to perform first practice about how to move a robot with a real robot that is down on the shop floor. Of course, this is a training course in general. I don't want to focus in any brand, robot brand, of course, but we have the practice are going to be performed in an ABB robot, right? After the first practice, we will come back here to have a coffee. We have a small time. And after the coffee, we will start again for the second part of this training. And we will start with the robot programming about how is the robot program structure. We will see how to manage the robot execution program. We will see one movement instruction. We will go in depth on this instruction, focused in this case with the AGV robot, which is the one we are going to practice at the end, this programming training. I wanted to focus on this ABB movement instruction more than in others, in other brands. And finally, we will see as well a robot programming sample, and afterwards we will go downstairs again to perform a small practice on how to program an industrial robot, an ABB industrial robot. So these are the contents. Go ahead. All right. Sorry. If any of you here on site or online, if you have any questions, please go ahead and feel free to ask me with no problems. Of course, I will try to answer you on my best. Okay. Okay. First, regarding the robot system, the first point, I would like to pay attention about what is an industrial robot. Regarding the robot definition, an industrial robot is a programmable manipulator with at least three controlled axes, able to perform a lot of different tasks. What I want to focus here is on these words: programmable manipulator. What is a programmable manipulator? It means that you can program this manipulator to perform different paths, different trajectories on the space. So you can change if you need to do it to improve or to modify some production process, right? So I want to focus on this. It's a programmable manipulator. The second one, what I want to focus is that it controls at least three axes. At least three axes. Why do we need at least three axes? Because, of course, the space where we move in is 3D space. So to move on this 3D space, we need at least three axes to move one object on this 3D space. If we have just only two axes, the only possibility is to move this object in a plane, on a space plane, right? Okay, that it could be, but it's not the most versatile possibility. Okay, and these three axes are controlled, always are controlled for something. What is controlled by is by the control system, okay? Is like a CPU at the brain of the robot is the one who is controlling this axis. Could be three or more, right? It's not controlled by a human operator, really, like we will see in the picture on the right. So these are controlled automatically by the control system. So this robot is able to perform a lot of different tasks depending on the tool attached to the robot flange. So finally, the robot is nothing more than like a mechanism, a device to move something. What do we want to move with the robot? It's a tool to perform some kind of process, right? It's not necessary. Sorry. The most important, finally, is the tool attached to the robot arm. So depending on the tool, we can perform different tasks. And what is composed this industrial robot by? This is composed by a mechanical arm and a control system, as I told you. Here on the left, we can see a small video of two robots. Let's see. Okay, these are two industrial robots working coordinated with an external axis, which is this turntable that helps in the arc welding process. This is a good example of what is an industrial robot working and how do they move, etc. And working as well together with an external axis. This external axis could be working sometimes in some robotic cells, but it's not necessary depending on the process, right? This external axis here helps a lot to get the torch, the arc welding torch, always pointing down to improve the welding seam features. Also, what we was watching here is what is an industrial robot. What is not an industrial robot is, for example, this one, the excavator on the picture on the right, because okay, it seems it's similar to a mechanical arm, but it's not the same because this mechanical arm is not controlled by a CPU, a brain, in an automated way, right? This is controlled by the excavator operator that is inside working with the different handles, right? So what I wanted to show you is the difference between a device and what is an industrial robot. Okay, now which are the industrial robot components? Okay, a naked industrial robot is composed by a manipulator, the mechanical arm, a control cabinet, which is here on the left, and a programming device, which is the teach unit. Usually, the robot, when our company purchase an industrial robot, usually it comes naked, as I told you, with nothing installed on it. So but this is not useful for our processing. If we want to use this robot for a kind of process, what we have to do is to get more accessories. Which accessories? Of course, the first and the most important is the tool. Okay, the tool which is attached to the robot flange, to the string of the robot. Of course, if we want the tool perform a process, we need, for example, electrical cables, hoses for water, for hydraulic hoses, pneumatic hoses, of course, depending on the kind of the process we want to perform with the tool, right? So all these hoses and electrical cables are grouped in a dressing pad with something that we call dressing pad. More accessories that could be mounted regarding a robotic cell regarding with an industrial robot. In this picture, we can see a track. It's an external axis where the robot is mounted on, and with this kind of accessory, we can improve the robot reachability, okay, to get to some spaces, to greater space in the space. So this is all the industrial robot components I wanted to show you, and to be clear here with this slide. Now, what is a robot arm configuration? On the left, we can see what is a typical and usual industrial robot configuration. That is the most common. The most common configuration is similar to the human body arm. As we can see, we could consider that the robot base could be our shoulder, and from this, the other joints could be similar to the human body arm. It's composed usually by 6 rotatory axes, driven by electric motors in each axis. Okay, so we have 6 axes, and in every single axis we have an electrical motor driven by by a device inside of the control system cabinet. Okay. And this is the most versatile configuration that we can find in an industrial robot cell. Other different configurations could be the other ones that we can see here, we can watch here on the different examples. On the A pattern, on the A picture, we can see as the same, the most common configuration, like our arm with 6 axes. Oh, it's not translated. Okay. Okay, and on the second one is an SCADA configuration robot, which is a robot with just only 3 axes. 2 of them are rotatory axis, and the other one is linear axis. This is a good example, for example, for picking and place small parts very quickly. So it's a good configuration to perform this kind of tasks of picking and place very quickly. All right. It's not so versatile like the before example, the sample before, but for sometimes, depending on the process we want to perform, we have to decide to use one or other configuration. The C example, what we can watch here is a Cartesian robot with 3 linear axes working. In this way, we can reach a large space to robot work in. And finally, on the D picture, what we can see here is a parallel robot, which it has 4 axes. 3 of them are, no, not 3. The fourth of them are rotatory axes. All right. This is a good configuration as well for picking and place of the small or medium parts, working very quickly in process of this kind of task. It works like a spider with legs, like a spider. It's very, very nice. Watching this robot working very quickly. So these are different art solutions or different art configurations I wanted to show you. The most versatile, as I told you, is the on the left, on the figure on the left. Industrial robot applications. Okay, an industrial robot can be used to perform almost any productive process very quickly, precisely, and with high accuracy. This is important. So, and finally, the robot's application is determined by the tool attached to the robot tool flange. This is what I told you before. The most important finally on the robot is the tool, because it's a device dedicated to the process we want to perform. Here I wanted to show you different robot applications, all of them depends on the tool attached to the robot flange. On the left, we can see a couple of arc welding robots working with arc welding torch for this kind of process. On the second one, we can see an spot welding robot with an spot welding tool attached to the string of the robot. It's very high. Usually, this kind of tools are very large, very impressive when you see that kind of robots working in automotive inside of cars with these huge tools inside of the car. On the third example, we have a manipulation robot with a gripper, a vacuum gripper attached to the robot. It's composed, as we can see here, by 4 suction cups. Okay, and it's able to handle box or any other parts we would like to work with. On the next one example, we have a gluing dispensing robot, which handles a gluing dispensing tool. It's usually for dispense glue on different parts to fix two different parts or to seal them together. Okay. On the next one example, we have a drilling milling robot with a milling device tool to mechanize parts in a factory. Okay. And finally, I wanted to show you as well a laser cutting process with a laser cutting head attached to the robot, performing this kind of laser cutting on, it seems, a metal plate. So if you have a tool, you can perform any task you can imagine with a robot, with an industrial robot. So it always depends on that, the most, all right? It's not always, because the robot has always as well the limitations, but the most important finally to the process is the tool. We continue with the robot system description. I wanted to talk now on this slide about the processes that can be robotized. Okay, at the beginning, when the robots started to work in industry, an industrial robot started to work to perform repetitive tasks in massive production systems where just one type of product or a few of them, okay, were manufactured repeatedly, okay, performing one task and another one once and again. This is very common, very usual to find this kind of processes in automotive, for example, where hundreds of robots work in the body white and the pressing lines, with hundreds of robots working, as we can see here on the picture of above. Okay, different robots working inside a car with, in this case, are spot welding tools. But nowadays, the new trend is to try to use these industrial robots in unitary or very short units production systems. But to get this goal, we need new technologies like artificial vision, and many other applications are being developed to avoid depend on the high-skilled robot operators. This is the most problematic for small and medium enterprises that like to use a robot inside of their production lines. To hire very or high-skilled robot operators. So this is the picture on the bottom. We can see an example of robot working in a shipyard where different parts, most of them maybe are different from one ship to another ship or vessel. So always this kind of programming a robot is not easy. So we have to start thinking on finding new technologies or applications like artificial vision to perform or to help to perform these kind of processes that are unitary and not are massive production. Okay, so I wanted to be clear this, where the robot should be focused on their task, their job. Okay, now, which technologies or ways we can program a robot? On this slide, I wanted to show you these different technologies. Could be more, of course, but I'm going to present you the most common technologies. Okay, if we want an industrial robot to perform a process, we have to teach the robot movements. To do that, we have several possibilities. The first one the most common some years ago was using the robot using the robot teach unit to perform this teaching trajectories, to teach the robot trajectories, moving the robot manually with the teach unit. We will see now. We can use as well robot simulator software to get the robot positions. Is another possibility. Another one could be use a part localization system like artificial vision. We will see on a video here to improve the robot accuracy from predefined positions that we could achieve from the teach unit or from the robot simulator software. And as well, the last one I wanted to show you is using other guide systems like hand guiding that we will see tomorrow on a training session here with another workmate. Okay. Now, please, we will pay attention to the video on the right above. This is a robot working on a production line. In this video, we can see two different possibilities to teach a robot. The teaching with a teach unit, or the other possibility is what in the video called lead through. Okay, if we want to teach a robot with a teach unit, what we have to do is move the robot to one position in the space, the position we wanted to save, to teach the robot. And as we can see here, the robot operator is working and moving the robot with the teach unit to the position, to modify one position or to improve one position teached before. And in every single position that he moves, can teach that position and save and modify a predefined robot trajectory. Okay, so the robot operator has to be besides the robot handling the teach unit. And of course, if you can see here, the production line should be stopped. Of course, can be working and can be start working in an automatic process. This is one possibility to program a robot using the teach unit. The other one is the lead through programming, where there is a tool attached to the robot flange, and between the robot and the tool, there is a device that is able to measure the efforts done by the robot operator, and the robot moves to the place the robot operator wants to lead, and finally can program the robot trajectory in that way. These are two of the possibilities to program a robot, with some advantages and some disadvantages, of course. The advantages are that these methods are easy to use. They are programmed quickly, and these are the disadvantages are that we have to switch off the production. We can't continue with the production in automatic mode, of course, and the robot should be besides the robot, and maybe the process is not very healthy or something like that. Okay, it's a little bit dangerous. So, okay. Another technology we could use to improve our robot programming is, as we can see on the video here in the bottom right, is the artificial vision to improve the accuracy of a predefined robot trajectories. The robot trajectories were programmed before. What it's doing now, the robot is trying to locate the starting point for the welding process. So this is another kind of technology for parts that are not that are free, are not fixed to a fixture. Okay, that is more common maybe in massive productions like I showed you before in automotive. Okay, on the picture here on the left, we can see different robot trajectories on a robot simulator that we can check there before translating these theoretic trajectories to the real ones on the robot. And this is all about the robot system. I don't know if any of you have any doubt so far. Okay, if not, we can continue. Okay, now on the second point, I wanted to speak and to explain about the robot movement within a 3D space. I want to give you these concepts before starting with the robot programming because this is very important to understand the robot programming and how the robot moves in a 3D space. After that, we can start to perform a robot programming correctly and with a good thinking of what we are doing or not. All right. So in general, right? Gets apart the robot. Now I'm going to speak in general about 3D objects. That really a tool in a robot is a 3D object, that we want to move. Okay, to move an object in a 3D space, in a Cartesian space, what we need reference to know how much and in what direction we want the object to move. So this is what we need, the references. To measure how much we want to move and displace this object in a 3D space. To do that, we use Cartesian coordinate systems as a reference. And this Cartesian coordinate systems is composed by one origin and three perpendicular directions, X, Y, and Z. Okay. Okay, starting before starting with the movement of an object in the space, if we want to move a point, a single point, no dimensions, right? No 3D dimensions. Okay, if we want to move a point in a 3D space, what we need is to know from this point are which X, Y, and Z coordinates are regarding to a reference system previously defined in any place we have decided before. Okay, so as we can see here on the left picture, we can see we can see here that there is a point in the space regarding to this origin. The point P has the dimensions of 4, 3, and 2 in the three different perpendicular directions, X, Y, and Z. Okay, this is for a point in the space. If we want to say that this point is in that point in the space. But when we want to move an object in a 3D space, what we need is not just the position of that object with the X, Y, and Z coordinates. We want to need as well how much it is rotated in this space, in rotation in X, Y, and Z as well. Regarding again to a reference system. Okay. To get to get calculus easily, we usually use an auxiliary reference system linked to the object. This auxiliary reference system moves totally fixed to our object. Okay, it's just something auxiliary that we use to facilitate us the calculus of the object position and rotation in a 3D space. We can see here the auxiliary reference system attached to the small plane here in the picture of the center. Okay, and in the picture on the right, we can see this auxiliary system and the position of the small plane regarding a reference system, and is represented all of this, not just the position of the small plane, but the rotation of the small plane by these six informations: X, Y, and Z displacements, and rotation in X, Y, and Z as well. So this is something that we have to be clear, right? About how an object moves in a 3D space and why we need this information. Now, the robot movement within a 3D space, the robot's tool really is an object within a 3D space, and we want the robot to move that tool along different positions, as we can see here on the picture of above, with or without not the same orientation. We can see here in the picture of above, the robot is moving. It's a sequence of movements of a tool starting from the point 1 to the point 6 and along a straight line in space, but with the tool in different with different orientations or rotations in the space, right? And this is why we can't. I wanted to explain to you how an object, a 3D object, can move in a 3D space. We have to consider not just the X, Y, and Z, but the rotation as well of the tool in that case. We use that information to define and program a movement trajectory of that tool with the robot. Okay, as we can see, and it's explained here in the test. A new delivered robot comes without any tool attached to its robot tool flange axis 6, as we watched before. So here on this picture, what we have is a naked robot with no tools, no accessories at all. And what we can find here on this naked tool are finally two references. One of them, the first one, is the robot base system, or World Object 0, depends on the brand of the robot. Some robot manufacturers call on that on one way or on the other. And this is a reference system with 3 directions, X, Y, and Z. And there is another, in that case, the reference system that you can see on the robot flange, on the axis number 6, is not a reference system, it's an auxiliary system, which is useful for us to understand how this axis number 6 is not is rotated, orientated regarding the reference on the robot base. Okay, this the auxiliary system on the robot flange usually we call it tool 0. Okay. Okay. If we want to know the position and the orientation of any robot tool fitted to it, what we have to read is this information on the teach unit. We can access to this information on the teach unit on a dedicated window. It depends on of course, on the robot brand. In this case, I have two pictures from the teach unit of ABB robot. And this, as we can read here, in this window, we can read the information of the robot position in two formats. One of possibilities to read the information of the robot position of every single robot axis in degrees. Okay, we have 6 axes, so we should find information of the 6 axes in degrees. This is the angular format. And the other possibility is to read this information of the robot position in Cartesian format. This information gives us the position in X, Y, and Z, and the rotation that the robot, the tool, the activated tool has in the space. Okay, on the left picture, we can see the information of a robot position, any, I will remember, of the 6 axes of the robot. We can see the information of the axis 1 till the 6. Right? Now, without moving the robot from that position, okay, we could, the robot can translate this degrees information to information in Cartesian coordinates. Okay? So, the same information, but in Cartesian, it can be found here on the right picture. In X, Y, and Z. Here, ABB show us the information of the rotation of the tool in a specific way that is called quaternions. It's not very meaningful for us, but it's very useful for mathematics inside of the control system. For us, it's more understandable. The rotation in X, Y, and Z, but this information can be translated automatically. So, okay, but ABB is the way to show us the rotation information is in quaternions. Of course, this information of the position of these coordinates are in that case, of the tool 0 that we can see in the parameters window, and regarding the word object or the robot-based word object 0 as well. Okay, depending on the tool that we select on this window, we can have this information or other different depending on the tool that we are selecting, and of course depending as well on the base reference. There are the two information that we need to select. Okay, let me review this. If we want to know position and orientation of any tool fitted to the robot, okay, now we are starting to work with a tool attached to the robot flange. The slide before I was showing you the naked robot, but now I wanted to pay attention when a tool is attached to the robot. So we have to define an auxiliary reference system linked to the real tool onto a particular point named tool center point. What does it mean? When we have a real tool attached to the robot, what we have to define on this real tool is a tool center point, a key point, the point where the process with the tool is going to be performed. For example, we have here different examples on this picture on the left with robot with different tools attached to a robot. The first one on here is a naked robot as well. We can see an auxiliary reference system of the tool 0, as I told you before in the slide before. On the besides, we can see a spot welding tool attached to the robot. The usual the tool center point is defined here in the tip of the cap of the spot welding tool, which is the point where the process is performing. Okay, this is the cap that is usually fixed, and the other one is the cap that usually open and close to perform the spot welding. Another example is here. It could be a water jet cutting tool, and of course the good point to define a tool center point, yeah, on the tool is on the point of the tool. Could be in another place, yes, but usually you are going to define this tool center point in the key point where you are going to perform the process, right? As you can see here, these tool center points are defined on physical points on the tool, but of course we can define these points not in a physical place on the tool, but on the air, right? As we can see here, we can see what we have here is a spray painting tool for painting cars, for example, or any other parts. And we could define the tool center point here on the tip of the spraying torch. Yes, of course, but maybe it's not useful for us. The most useful is to define the tool center point of this physical tool, real tool, in a distance where maybe the blade is going to be present when we start to spray, right? So we decided to define this tool center point on the air, not in a physical point of the tool. So these are some examples that I wanted to show you. Let me continue reading this information on the test. With this information, the robot is able to calculate the position and orientation of this point on the tool and can be read by an operator from an indicated window on the teach unit, the window that we saw before on here, on this window. On this window, we could select, for example, not tool 0, but other one that we have defined before, right? So, for this tool center point, what we have to know is in this schematic that we have here in the left picture, I wanted to represent schematically a tool center point TCP defined regarding to the tool 0 point on the robot flange, right? What we have to know is from this point, which is the distance to the till the tool 0 and the rotation, etc. This is something that is not in the scope of this on this training, because we have only 2 hours of training. Is not enough. But I want to have you this idea in general, and afterwards maybe in the future you have another training course longer, and you can focus these ideas better on the robots programming and robots handling. Okay, this is for a new tool attached to the robot flange, but we also can define different base reference to the robot. We started with base reference, the work object 0, attached to the robot base when the robot is naked. But when the robot is starting to be integrating in a robotic cell, there are going to be different fixtures or different parts or different robots working together in the same robotic cell or with different devices like artificial vision. So to improve our programming, we can start working with more reference systems more than the robot base. For example, I wanted here to represent on the right picture another user base here on this cube, which is always regarding to the robot base. The information of this user base is always regarding to the robot base information. And this is helpfully, as I told you before, for example, when another robot is working together with the first one, because if we want to these robots don't collide, we need to know where are these robots working against each other to avoid any collision. So they have to handle the same system coordinates, the same reference to know if they are going to collide or not. Of course, if we have this artificial vision system, we need as well to work together. The artificial vision system and our robot should have the same robot reference. To do that, we use user-based reference defined in a point where we decided to do. Okay, trying to be helpful for us. So, as you can see, we started from a naked robot with different mathematical tools, different reference systems, auxiliary systems as well. Now, when we are dressing our robot with different tools, we started to define different mathematical things like user bases and new tool center points. Okay, and this is about the robot movement within a 3D space. Now, I want to pass to the point 3 about the moving a robot. And how we can move a robot in a space. Okay, a robot can be easily moved in two specific different ways. Okay, if we use one, we can't use the other one. Okay, this is why I wanted to say exclusive. But within each of these two possibilities, there are two options to execute movements, because we can maybe move the most easy way about to speak about robot movement or really tool movement is tool translational movement. Okay, but we can perform as well not just translational movement of the tool. We want maybe we can perform rotation movement. Okay, so there are both. There are two ways of moving a robot, of moving a tool on the robot. Okay, fitted to the robot. To move that tool in a 3D space or with translational or in orientation, we can use two different ways. The first one is using weather dedicated movement buttons on the teach unit or a joystick. It depends on the manufacturing brand robot. This option allows to the operator to move the robot tool from one point in the space to another point in besides X, Y, and Z or rotation, right? To teach and to save that position in the robot controller. When the robot operator moves the robot to one point, is usually to save that point, this new point on the robot program. Okay. So this is what I wanted to say, that is to teach and save the position in the controller. The operator now is working in manual mode with the teach unit and is working besides the robot. Okay, maybe we can switch off the heating system.
Yeah.
I'm starting to be, and people maybe starting to be low. Okay. Thank you, Mari. Okay, so one possibility to move the robot is using the teach unit, moving the robot with the dedicated buttons or with the joystick. Another way is executing a program with movement instructions inside of it, with positions previously teached. Now, what the operator does is execute the program, whether in that case, whether in reduced speed mode, manual, we can say, or whether in fast speed mode, in automatic. So what I wanted you to understand is that these two ways of moving the robot, okay, or executing a program, or moving the robot with the joystick or the buttons. And both for maybe for translational or for orientation movements. Okay, and if you are moving the robot executing a program, you can't move as well at the same time this robot with the buttons or with the joystick, just the contrary. Okay, robot movement types. So far, I was trying to explain you this kind of movements. Now we are going to see these movements on these GIFs that I could get. These GIFs, we can see the robot movement of each axis independently, because the robot can move the axis independently one from the other. We can start from the axis. Oh, sorry. Okay, where the robot can move, we can start with the axis number 1 of the robot base. We can see there. The axis 2 is moving on that way, on this tip. The axis 3, 4, 5, and 6. But the robot can also move the tool in different ways, moving the 6 axes at the same time in a convenient way, as we can see on the gates below. On the left, we have here the tool orientation. What we can see here is the tool center point that is fixed on the space, but the robot is able to perform movements of to get a different orientation of the tool without moving the tool center point. This is a tool reorientation that we call it. It's something very impressive when you see the course for first time doing the robot this kind of movement. At least for me, it was long years ago. Another kind of movements are the linear movement. Robot on the next GIF, we can see the robot performing this kind of linear movement. For doing this, the robot needs to move the 6 axes at the same time, of course, in a convenient way. Now it's impossible to perform these movements without moving these 6 axes at the same time. Some of them are going to move quickly, other more slowly, and maybe some of them are going to be moved with more wide or less, but finally it needs to perform to move the 6 axes at the same time. On the next GIF, we can see also the robot executing movement in parallel to some directions in the space, in that case to the robot base reference. Okay, we can see the robot moving in linear movements. And finally, the last GIF on the right, we can see the robot performing as well this linear movement parallel, in that case, not to the robot-based reference system, but to the robot tool reference system that is attached to, in that case, to the tool 0. Okay? And these are the kind of robot movement types that we can perform with the robot, whether using the joystick in a manual mode or the buttons, or executing a robot program. Now it's time to go downstairs to check all of this theory in a practical mode. What we have here is this is an ABB robot. This is 6,660 ABB robot. Now there is almost no tool here. It's just a small gripper tool attached to fitted to the robot flange. There is as well a small joystick here. This is for the practice for tomorrow for the hand guiding. This is the dressing pack as I showed you before to connect all the tools that we want to install on it. What we can see there behind, for the people who is online maybe can't see it, let me move the robot to show you an external axis. Okay, this is an external axis. Really have two axes, rotatory axis, rotational axis, to improve the robot richness for some parts that we want to process on there. This is the control unit, the brain and the brain of our robot. And this is finally our teach pendant, the teach unit, from where we can move the robot and program and so on. Okay, this is the teach unit, the real one, from where we can select different windows from there. Oh, no se puede poner aquí encima y enfocar así hacia abajo. Igual es más, pero bueno, aún así es que no sé. Sí. Okay, this is the joystick. In that way, this is the joystick I'm going to use to move the robot. I'm going to show you how to do. And maybe if any of you want to move and try, you can do it. It's not dangerous because now the robot is in manual mode. It's going to move in slowly mode, right? So first, what I have to do is, for helping me on the moving of the robot, is to select the dedicated window about which is the position of the robot here. To do that, what I open is the movement window. And from this, we can see the same window, dedicated window that we could watch upstairs. All right. Now, I'm going to perform selecting the movement of just only the three first axes of the robot. Like this is a joystick. This joystick has only three freedom degrees, so I only can move three axes of the robot. So to select the other three axes of the robot, I have to change here, pressing another button, right?
So if I want to move axis number 1 from the base of the robot, this is the movement from one side to other side. This is analogic joystick. As much as you lean the joystick, the robot is going to be faster or slowly. If you hold off the joystick, the robot stops moving, right? This is the movement of the axis number 2, the movement on the axis number 3. Now I switch for robot for axis number 4, 5, and 6, pressing here one button, and now I can move the axis number 4, number 5, and number 6. And to perform the same movements but in linear, for example, I have to switch the mode from single axis to linear movements, pressing here one button. On this way, I can perform linear movements, for example, in that way, in X, in that direction, or in the other one. In this one, the robot is moving the 6 axes at the same time, one of them faster and the other a little bit slowly. On this way and on this way, maybe we can go up or down movement. And of course, we can perform rotation, but here in this robot is not defined any tool center point more than the tool 0. The rotation of this robot tool could be only performed in that tool center point, which is in the center of the axis number 6, right? So I'm going to change to reorientation. You have to imagine that there is a point here in the center of the axis number 6 that it's totally fixed in the space. It's not moving. The coordinates S, Y, and Z of this point is always the same. Just what only changes is the orientation. So I can perform this kind of rotation to adapt the tool to go, for example, in that way. I have to go to a point here, but to be able to handle some part, this is not a good orientation. So I achieve the position of almost near the final position, and when we are close, and besides, we can select the correct orientation of the tool to engage with the part I want to handle, to grasp with the robot gripper. Okay, as you can see, the robot moves faster or slower depending on how much I lean the joystick from one point to other. And again, when I on the good position, I can go slowly and teach and save the position to make a robot program to perform a trajectory in the future. So this is the way that we can move a robot. In manual mode, another way is performing a robot program. We will see it after in the second practice. If any of you want to work and to try, yeah, go ahead, Maurice. Yeah. So what you have to no, are you left, right-handed? All right. Try to put on that way. With these fingers, you press here the safety, and now the robot is motors on, and you can start to move the robot with the joystick. We can start changing the mode from here, pressing this. Okay, you can see that the information is 4 degrees for independent axis movement. Try to move in that way or in the other. It's very easy, very very, how to say, intuitive. Yeah, really. It's like playing like with the PlayStation or something like that. Youngest people are easier, better performance than me, for example, doing that. Yes, if you want to change for linear movements, you can do it. And you can realize that the movements are different. Okay. Okay, we can decide when we want to teach one point in the space, we can decide to go to this space moving each axis independently or moving the 6 axis with linear movements. It depends on us. Okay, of course, the most quickly movement is with independent axis if we know which axis we have to move. If not, if not, we can use linear movements. Of course, when we are near, besides the part where we want to process it, we have to perform linear movements that are more accuracy and more understandable and intuitive to understand how the robot is going to move. So I think it's easy to move. Okay, I need more practice, of course. We should have here at least for 2 hours moving a robot, more time, each of you. But okay, do you want any of you? Yeah, try. Okay, you are handwritten. Yeah. Okay, so go. Okay, in that way. Okay, this is the safety to start the motors. Push. No. Okay, push. No, sorry. Confirm. Yes, you have to hold on. Now is motors on, so you can start move the robot with moving the joystick. In one way, in another one. If you want to change for orientation, you can do pressing one button there. For orientation is that. This is linear, and orientation is switch from one to other. It's very easy. You have to pay attention to avoid to collide. Moving, if you move a lot, the axis, for example, in that case, number 5, you could collide the joystick with the robot arm. So you have to pay attention always when you are moving the robot to avoid any collision with inside of it, the robot, or with other parts, right? Go. Yes, because if not, the dressing pack is going to twist. Oh yeah, maybe because you are in the limit, okay, of one axis, you have to try to move to another way. No. In that way. Okay, the most intuitive is moving it, of course, linear. Or if you want to change to rotational and independent axis, you can try to do it. And you can move with the independent axis mode, you can really move 3 axes at the same time if you are able to move the joystick in the 3 different freedom degrees. Yeah. No. The only way if you save that position previously in an instruction program, for example. If not, it's impossible. The robot remembers the previous position. When you have a collision, yes, the robot really is saving all the trajectory or the movements, and he tries to move against when you collide with another part against this part, because remember the direction from this point collision enters into the collision, so moves away from the collision. He tries, but not always. Okay. Okay, you're welcome. Lorena, do you want, please? No? It's very easy, really. Yes, try. hand right, yeah, sorry. Go this right hand over here on the strap. You have to press and to push this. This is a safety device. Okay, now is, okay, let me confirm. Okay, now it's okay. Try to push not too much. Okay, this is good. Now motor's on, and when you start to press the joystick, the robot moves. And faster as much as you lean the joystick from one side to another side, right? It's finally it's very easy. You need more practice, of course, when you are near or besides the part where you want to process. If you want to change, for example, for the linear movement, we have to push here, and you can see here that the information is changing and the movements are different, of course. This is orientation. Yeah, orientation. This is linear, sorry. Come here, okay, for example, or away is very nice. Okay, you're welcome. So I think that's all for this first practice of the first training session.